Okay, so we will now begin Unit 5, and this is on DC machines. I have the lesson prepared in 3 parts, and if we are able, we may be able to do part 1 and part 2 today, and then the other part next week. But let's see how it goes. So this first part basically is a kind of general introduction to DC machines. And the machines include, when we talk about DC machines, rotating machines, we are talking about motors and generators. So we will look generally at their construction and their principle of operation, and then later on how the EMF is developed in the machine, both machines. All right, and I have some work examples included and some questions for you to do also. Just let me know if you're hearing me okay, because I'm not so sure about my headphone mic.
Sound a bit different than usual, but it's all right.
Okay. All right. Let me see if I can get closer to the computer mic. All right. So the machines, as I've said, are basically of 2 types: motors, generators. And you know what motors do? They convert electrical energy into mechanical energy, and generator, the opposite, converts mechanical energy into electrical energy. Now, the same machine can be used either as a motor or as a generator. And to the right, you will see a drawing of what the machine looks like, with the different components. So there's an armature with armature windings. So the armature, some people call it the rotor because it rotates. But there's actually a definition for armature. And an armature doesn't necessarily rotate every time. And different parts of the machine, you have field windings around field poles. And the core is made up of some electromagnetic type of, well, ferromagnetic material. And you have what is called a yoke, this circular part, which is not magnetic, but is therefore supporting the whole frame of the machine. Right. Then there's another important part of a DC machine, the commutator. And of course, the machine rotates, so there's a shaft and there are bearings there to facilitate that. To get current into or out of the machine, you have brushes that will be connected to either supply voltage or to a load. But we'll go into more details with in these. All right, persons are continually joining, so hence the interruption. All right, so a little bit more closer view of what we just spoke about a while ago. The poles. So notice now, well, in this drawing here, we have 4 poles, a north, a south, another north, and another south. So the poles are always going to be in pairs, right? So you can always have a pair of north and south, or pairs of north and south. These poles are actually electromagnets. Right? So windings, conductors are wound around them in such a manner as to create north poles and south poles alternately. So a DC current would be flowing through the windings. And if you use your right-hand rule, you can determine which pole is north and which pole is south for yourself. This round section now would be the armature, and it has slots in which conductors are also situated. So these are the armature conductors, these dots here in these, between these slots. On the shaft also is something called a commutator, and it has a very important role in the DC machine. Basically, it converts an AC created EMF into a DC output. And that output current or input current would be sent into the commutator and then into the armature via these brushes that are situated resting on the commutator. All right, and then we spoke about the yoke before, and we said that it provides support. Now, there's also a shaft here, and this circle here in the middle here is representing the shaft. So the shaft would rotate, and with it, the armature conductors and the commutator. All right, now how is the, let me let in somebody again. How is the machine able to create a voltage? All right, so basically we're looking at the principle of operation of the DC motor. All right, so remember what motor does. It converts electrical energy into mechanical energy. So some current now will be going into the armature conductors via the commutator. So we have, in this elementary machine, we have one coil, and the coil is made up of 2 conductors, right? So you can imagine that the conductors split somewhere along here, right? So 2 conductors, 1 coil, 2 conductors. Now, when the current leaves the battery, it flows through the brushes, through the commutator, and the conductor is connected onto the commutator. So current flows through this conductor and through the other conductor and back to the other end of the supply. All right, now as current flows through the conductors, you have magnetic fields being created around the conductors, as you would have been aware by now. So as a current flows through, there's also an associated magnetic field with the current. All right, so both conductors have magnetic fields around them. And the field, the magnetic field created by the field poles, which could be permanent magnets or the electromagnet that I showed you before with windings around it. It is producing, that field now is producing a magnetic field that moves from north to south, as usual. So you have a magnetic field between the field poles. You have another magnetic field around this conductor, and you have another magnetic field around this conductor. Now, based on Fleming's left-hand rule, we can tell the direction in which the conductors will move, once a current is flowing in the conductor and it is inside a magnetic field. So the direction of rotation, because it's on a shaft, this one moves up, this one moves down, and because they're on a shaft tied together, they rotate. So this will always be the direction of rotation once the supply voltage is oriented, as you see there. All right, so that is basically how we get the motor to operate. Basically, current carrying conductor or current carrying conductors within a magnetic field will cause the motion, and since the conductors are mounted on a shaft, they will rotate. All right. We can also look at the principle of operation of a DC generator. All right, so again, another elementary DC generator is shown to the right. Now, the generator basically converts mechanical energy into electrical energy. So initially, there's no current in the conductors, right? But by some means, we will rotate the conductors. Now, that mechanical device that rotates the conductors is called a prime mover, and it could be something like an engine, a diesel engine, or another motor. Or for large AC generators, it could be a steam turbine, a hydro turbine, so that kind of thing. So what the device that causes the mechanical action is called a prime mover. All right, now this conductor, which is not carrying any current, is gonna be rotated in the magnetic field. And as it rotates in the magnetic field, we have the conductor cutting the flux, and as the conductor cuts the flux, you would remember that we have an induced EMF across each conductor. All right, so and then those induced EMF add together to give you an output EMF at the terminals of the machine, right? Now, if a load is connected here, then a current will start to flow in the conductors also. But without any load connected, you have an induced EMF across the conductors, which is available at the terminals of the machine. All right, so basically that's the principle of operation of the DC generator. The a conductor is moved, in this case rotated in, our conductors are rotated in a magnetic field, and because of the flux cutting action, you have an induced EMF across the conductors, and that induced EMF is available for output. Now, you will probably realize that an AC voltage is actually being induced here as the conductor moves across, right? But the commutator now is similar to a rectifier. So it's a mechanical rectifier, and it converts that AC voltage that is created into a DC output across the brushes. All right. All right, so this is now giving a little bit more detail as to the creation of the DC output. Somebody is saying something. Ah, all right, very good. Right, right, Mr. Adams. Right, so it is like this. You see now for the two conductor situation where we only see the positive half cycle being reproduced due to the commutator action. Right? You can read through this and basically see what happens. So this is the output for two conductors as the, and well, you would have known from before, but maybe we should just go through. So as the conductor is moving through different positions, it is actually producing an induced EMF. So in this position where the conductors are in parallel to the magnetic field, moving in the same direction as the magnetic field, or in the same direction as the magnetic field here, there's no induced EMF. So this would be at position A. But when it turns, let's say it turns a quarter cycle, so this red conductor now is here. It is actually cutting the flux, maximum flux cutting taking place. So maximum induced EMF occurs right there. Then it starts to decrease as it goes down and it reaches zero. But because of the output of the other one now takes over, and you see that, right? So we don't have anything going negative as we would be used to in an AC, because the commutator is there now that ensures that when this conductor comes over this side now, the direction of the current actually changes. Right? So we have that induced EMF, and both of them are, so it's a rectified AC now. If there are more conductors, then you have a better DC profile. So this is the output for 4 coils. So instead of 2, we have 4 now. And so you can see now it starts to look even better. More like a DC kind of output. Right? So it becomes more uniform and a steadier DC output. So faster pulsation. Okay. Now in a machine you'll have hundreds of coils, right? Hundreds of conductors. So the profile would be even more uniform across here. All right, so we're gonna look now a little bit at, well, maybe not a little bit. We're gonna look at the construction of the machine. So we're gonna look at each part. So there are poles. So in this machine, we have 4 poles, right? And they're attached to a yoke. And the poles are made of steel, riveted together and bolted to the yoke. And notice now that there's a curve here that is called the pole tip. And that is there to help secure the field windings or support them, right? And also to increase the cross-sectional area of the pole itself. So you have what? A lower reluctance in the air gap. So there's an air gap in here. All right. And we mentioned before that depending on how the windings are wound around the pole, you get a north or a south pole. And these are actually wound in such a way that the poles beside each other are alternate. One north, one south, another north, another south. All right. Now, the flux actually flows through from the North Pole into the South poles, right? So from this North Pole, N1, into S1, some of the flux goes that way. And in the other one, from this one, it goes into S2, right? So flux going in both directions. And the same thing happens here. For the other North Pole, N2, flux goes to S1 and S2. So the dotted lines are indicating the travel of the flux through the machine. All right, remember we said that the poles does not necessarily have to be electromagnets. It can also be permanent magnets. But with your electromagnets, you can create stronger poles, stronger magnetic fields. All right, so yeah, that will be for the poles and the field windings. This is how the commutator is constructed. So yes, it's composed of copper segments, sorry, which are insulated from each other. And the insulation would be mica. Right? The commutator is mounted on the shaft, and the armature conductors are connected to the commutator segment. So you can see the segments of the commutator here, right? And in between them, where you see this line, the lines that will bear the insulation material is the mica. All right, so the basic purpose of the commutator is to make sure that current always flow in the same direction in the conductors. So each conductor is connected to the commutator. Now the armature winding and the armature itself. So again, the armature now is made up of laminations, and you can see the sizes here, 0.4 to 0.6 millimeter thick. Each of those laminations are insulated from each other, and they have slots on the periphery at the armature, so at the outer end. So you have slots to accommodate the conductors. So in this one, you see where you have two conductors in each slot, right? But you can have more than two. So an example here, if there are 40 slots and 8 conductors per slot, you would have a total number of 320, 40 times 8, 320 conductors. So the armature conductors now are the active part of the armature winding that is cutting the flux.
Tracing is almost rendered redundant.
All right. I hope none of you are getting redundant, Mr. Brown. All right. So
No, sir. Just the press release or the press conference. Sorry about that.
okay. All right. So you are there now?
No, sir. It was actually on the radio, so I'm actually in class now. Hoping not to be distracted anymore.
Okay, sir. All right. So the active part of the armature conductor is a part now that would be cutting the flux, right? And you would have an induced EMF across that part, right? There's something I think we mentioned useful flux when we were talking about mutual inductance. So the useful flux, it will be those that are linking the armature conductor, right? Passing through the armature core and linking the armature conductor. All right. So useful as opposed to leakage, which would only be cutting, say, the field winding conductors alone. And usually our calculations are based off the useful flux, right? So I think later on we'll do some calculation to determine the induced EMF, all right? All right, and as we said before, flux move from north to south in both directions, north to south. Okay. All right, so this is showing again a little bit more detail of how the armature conductors are situated in the slots. So the dotted line, all right, so what's happening? So maybe we start here. No, maybe, start on the left. So conductor 1 is here in this slot. It's the outer conductor in this slot number 1. And you can see the dotted line that the conductor is tracing, and it completes its journey in slot number 4, but it's the inner conductor in slot number 4, and then it will be joined back again with conductor 1. So this is probably a better view of what's happening there. Conductor 1 moves like this. There's a twist up here to allow it to come into slot number 4 here, right? And it is joined back here, right? So two conductors, conductor 1 and conductor 1 prime, joined together and are fitted in slot. And we'll mention something more about this, but I can probably tell you now. If this conductor is under the North Pole, then the other conductor that joins with it, this part here, to make the loop, the coil, is under the South Pole. Oh, and we can see it right here also. So conductor 1 is under N1, and the other N now, 1 prime, is under S1. So all the conductors are constructed in that kind of manner too. So you can have each of the conductors forming a coil on one on the North Pole and one on the South Pole at all times. All right. Yeah, so this is some more details of the same thing. So but I'll go back through it. So it's just another way of this one up here basically. The A is basically another way of showing it. All right. So the construction information, it's there for general knowledge. You practically won't be using it in this module, but it's just to give you a picture of how it is situated. All right, and then I have gone in a whole heap of details to give you that kind of view because the textbooks, the Hughes especially gives you a lot of detail, but it might be a little bit complicated for those who want complete general knowledge. It is useful to read it and also to read the Wiley about the construction. But I've tried to, as much as possible, simplify what is there in this in these slides. All right. All right. So the conductors, the armature conductors, can be connected in two ways. Generally, one is called a lap winding, and one way is called a lap winding method, and the other one will be the wave winding. All right, so in the lap winding, the ends of the conductor are connected to adjacent commutator segments. So each coil has one conductor connected to, let's say, this section of the commutator, and then the other end. This actually is a two-turn coil. So the other end now is connected to the adjacent segment of the commutator. So that is for the lap winding. For the wave winding, the two ends are connected far apart. So the segments to which they are connected are far apart for the wave winding. All right, and then this again now is basically explaining the connection of the lap and the wave wound. So you can read up on this. It basically would be giving you maybe a closer picture of what is happening with, say, the lap winding and how the connections are actually made. And the same thing also for the wave winding, right? So notice again, conductors, one conductor is under the North Pole, and the other conductor connected to that coil is under the South Pole. All right, so this is just basically general reading information. All right, and I've gone into some detail here also for the wave winding. Same kind of thing. So you can read it. You won't be examined on this particular aspect, maybe except to say that lap windings are connected to adjacent segments of the commutator, and wave windings are not. They are connected far apart. All right, now in the armature, you have a lot of conductors. So Z is the number of armature conductors. That is the number of armature conductors, and the conductors are connected in a kind of series parallel fashion. So the number of parallel paths will depend upon whether or not the machine is lap wound or wave wound. Right? The number of parallel paths is called C. All right, so the number of conductors that are connected in series per parallel path is equal to Z over C. So C is the number of parallel paths, Z is the number of conductors. So as we said now, the conductors are in the armature are connected in a series parallel manner. So the amount of conductors that are in one parallel path are the amount of conductors that are connected in series in one parallel path would be Z over C. Now for the lap wound, C is equal to the number of poles. So Z over C would be equal to Z over P. And for the wave wound, C, the number of parallel paths would be equal to 2. So 2 parallel paths in the wave wound machine. And in the lap wound machine, the number of parallel paths is equal to the number of poles. All right. And that is something that we're going to come back to when we develop the equation for induced EMF. All right. Now, brushes. Remember, we said that brushes are resting on the commutator segments. Right. So as the commutator rotates, it slides on the brushes. And the brushes are made of carbon, which have good conductivity. And they're soft enough so that they will scratch the commutator. I've made a note here that sometimes we say brush, but it could be more than one brush right here. Right? So it's called a brush set, and that may be composed of maybe one or more brushes. Right? So there's a brush set, not a brush set. But for simplicity, we just say a brush. So there are 2 brushes here. Now the number of brushes basically would be equal to the number of poles in the machine. Right? And you will notice now that some brushes are connected to the positive terminal. Right? So equal number of brushes are connected to the positive terminal, and an equal number is connected to the negative terminal. So this would be our 2, 4, a 6-pole machine. 2, 4, 6. So there are 3 brushes connected to the positive terminal and 3 connected to the negative terminal. All right, so this is something, if we were in the lab, we probably would see it. If the brush is not making good enough contact with the commutator, you may have some sparking at the brushes. And the sparking will increase when the loading on the machine gets higher too, because more current will be drawn. All right. Now the brushes are held in place by springs to ensure that you have proper pressure on them while they are in contact with the commutator. All right, so as I said before, the number of brushes is equal to the number of poles. All right, so we spoke about that already. All right, so you can read this. Right. Yeah, well, a point to note here is that the brushes are positioned halfway between adjacent poles, right? So you remember adjacent poles would be a north and a south. It would be normally placed in a neutral position halfway between them. So basically the commutator that is passing under that brush at that position would have no induced EMF at that position. But other conductors in the machine now would have induced EMF in them. All right, so this is basically explaining all of that again. All right, just another example of a 12-pole machine. All right, so 12 brushes, and there are a whole heap of commutator segments. So 12 brushes, 6 connected to the positive, 6 connected to the negative. And so this is a more general reading. All right, so let us look now at the development of the EMF equation in the DC machine. So I have drawn here a hypothetical machine which has only one conductor. You probably can see it right here. So there's one slot and one conductor. So you know it's not a real machine, but basically I've drawn it this way to explain how the EMF is created in the machine. All right, so all right, so flux, I guess, as before, is flowing from N1 to S1 and from N1 to S2, and also from N2 to S1, N2 to S2. Now, the flux that the conductor will be cutting is called the useful flux. So the useful flux per pole is equal to phi. Somebody has their microphone on, so it might be a good idea now to turn off your mics. All right, now let's say the armature is rotating at n revs per minute. So n revolutions per minute. So that would be n revolutions in 60 seconds. So the time for one revolution then would be 60 divided by n. So the time for one revolution is 60 over n seconds. All right, so n, remember, n is in revs per minute. Now, in one revolution, the conductor will make a flux linkage at each pole. So the conductor is moving, let's say it's going clockwise, as indicated by this arrow here. So the conductor, when it reaches this pole, it makes a flux linkage, another flux linkage here, another flux linkage here, another one here. So in one revolution, it makes a flux linkage at each pole. So the number of flux linkages would be P, the number of poles, times the flux per revolution. I remember what we did from before. Flux linkage was when the conductor cuts the flux. So we had used in transformers, we had used it as N phi. All right, now in this case, now it's one conductor. And it is making a linkage at each pole. So the number of flux linkage per revolution would be P the number of poles times the flux. Now, it is usual also in the textbooks to, instead of saying the number of poles, they say the number of pairs of poles, because a pole, of course, cannot exist by itself. There's always a pair, right? So the number of poles would be equal to 2p, where p would be the number of pairs of poles. So it is usually written this way also. But in terms of calculation, it really doesn't make a difference whether you use capital P or common P, once you use the formula properly. All right, so we're saying that in one revolution, the conductor makes, that single conductor makes 2p phi flux linkages per revolution. All right, and I'd remind you a while ago about Faraday's law. E is equal to nd phi by dt, but more technically is the flux rate of change of flux linkage. So it's d into n phi divided by dt. But since n is a number, we can take it out. N is a constant, I mean. We can take it out and just leave the factors that are changing. So n d phi by dt. And remember, n phi is the flux linkage. So if we relate what we have to the machine, n phi would be equivalent to 2p phi. And remember, 2p, the small p now is the pairs of poles. So 2p phi flux linkages in one revolution. All right. Now, the change in flux linkage in one revolution then would be dn phi, which would be 2p phi minus 0. So we start out with no linkage. So the change of flux linkages would be, which would be this part here, nd phi, 2p phi. And the change in time in time for one revolution, as we worked out earlier, is 60 over n, 60 over n seconds. So if we substitute those two now into the equation, Faraday's equation, E would be equal to 2p phi divided by 60 over n, or 2p phi n over 60 volts. So that is the induced EMF in one conductor. So the induced EMF in one conductor is 2p phi capital N over 60 volts. Or, so remember N here is in revs per minute. I could write it in terms of revs per second. So divide revs per minute by 60, it becomes revs per second. So, and then that becomes small n. So 2p phi small n, give me an equivalent value for the induced EMF, but small n is in revs per second. All right, any questions there? No, I guess not. All right, so that is the induced EMF for one conductor. Now remember we said that we have in each parallel path, there will be Z over C conductors. So remember the armature conductors now are connected in a series parallel kind of manner, where Z is the number of conductors and C is the number of parallel paths. So the number of conductors that are connected in series in each parallel path would be Z over C. So if the induced EMF in one conductor is 2p phi n over 60. In that parallel path, the induced EMF in all of those conductors would be 2p phi n over 60 times z over c, where z over c is now is the number of conductors in the parallel path. So imagine that you have some batteries in series. So you have 6 1.5 volt batteries in series. So one battery will represent the induced EMF in one conductor. So if there are 6 batteries in series, you're going to be multiplying that induced EMF in one conductor by the 6, right? So that is basically what's going on here. So the number of conductors that are connected in series times the induced EMF in one would give me that induced EMF for the parallel path across the armature conductor. All right, so I could write it in terms of revs per minute divided by 60, or I could have it in terms of revs per second. Right? So these two again are basically the same. All right, so remember now that we said for a wave-wound machine, the number of parallel paths is equal to 2, while for a lap-wound machine, the number of parallel paths is equal to the number of poles, or 2 times the number of pairs of poles. All right, so if we include now what C is equal to in the equation, then we have E is equal to 2p phi n over 60 times z over 2 for the wave-wound machine. Right? And if you simplify this, then you can get the 2's cancel here. So so p phi n over 60 times z. Or if I want to write it in terms of small n, it comes down to this. The 2's cancels again. And then it's p phi n z. All right, so either method of writing, you write it in terms of revs per minute or revs per second, you get the same answer basically. All right, now for the lap wound is, again, we substitute the value of C. C in this case now is 2p. And so the 2p's here cancel. So we're left with phi n over 60 times z, or phi nz. You can follow the derivation down to here. All right, so we have equations for induced EMF in the DC machine. Now, the induced EMF, E is called the generated EMF in the generator, the DC generator, while in the DC motor is called the back EMF or the counter EMF. So in some textbooks, you will see written as counter EMF, but the usual way of describing it is called the back EMF in the motors. All right, now if we take a look at this induced EMF equation, we will notice that some parameters are fixed for the machine. So for a particular machine, the number of poles would be fixed, the number of conductors would be fixed, and the number of parallel paths would also be fixed. Right? 2 and 60 are also constant. So basically you could say that they are fixed also. So I could reduce the induced EMF equation to K phi n, because phi and N are things that can change, but the other things are fixed for a particular machine. So E is equal to K phi N, where K now would be equal to these fixed parameters of the machine. K is equal to 2P times Z over 60C. So E is equal to, it can be written simply as E is equal to K phi N. And we're gonna use that kind of relationship in our calculations and in a further analysis of the machine. So I could write it in terms of the revs per minute or revs per second also. So E is equal to K phi small n. So I want you to observe that the induced EMF is proportional to the flux, and it is proportional to the speed of rotation of the armature. And remember that the flux is produced by the current flowing in the field winding. So the current flowing in here is what produces the flux. Right? So flux is going to be proportional to the field winding current. All right. Now for a particular machine, since E and phi and N can vary, so induced EMF can change, the flux can change. If I change the field winding current, the flux will change. The speed can change. Putting on load on it can change the speed. So that induced EMF for a particular machine, E1 would be equal to K phi 1 N1. So because phi 1 and N1 can have different values. Right. And E2, another value of the induced EMF in that machine, equal to K phi 2 or N times N2. I could divide these two equations and to get a relationship like this. And this can help me when I'm doing some calculation, like say, what is if I want to find out what is the new induced EMF if I change the flux or if I change the speed or any one of these parameters, I can determine a new value if I make some changes to other parameters. So this relationship is going to be useful. The K's are here also, but they cancel, right? So bear in mind that the K's cancel right there. So technically, I should have put the K's here first and then cancel them to show you for completeness. All right, here is a couple examples of how we can use the induced EMF equation. All right. All right, so let me give you a chance to read it, about a minute or so, to read the question. You can start with this one by Bird, from the Bird textbook. All right, so you'll see that it is a fairly simple problem. So the question says, a 4-pole wave connected armature of a DC machine has 750 conductors and it is driven at 720 revs per minute. If the useful flux per pole is 15 milliwebers, determine the generated EMF. By the way, what kind of machine would this be, based on the question that is asked?
Generated.
How you know?
So the generator determines the generated EMF, right? Which means that, yeah.
All right. I think another clue is also it is driven.
Yeah, right. An external force.
Right. So it is driven at 720 revs per minute, right? So remember that generated EMF, well, that is the term that is used for generators. And that same E, the same formula, will give you the back EMF in a motor. All right. Now, so as usual, we'll look for data in the problem. So the number of poles is P equal to 4. And that means that the number of pairs of poles would be 4 divided by 2. The speed is 720 RPM. The flux, useful flux per pole is 15 milliweber, so 15 times 10 to the minus 3 webers. Z is the number of conductors, 750, and is wave connected, so C would be equal to 2. So basically what we do now is to just put in the values into this equation. So 2P is 2, phi is 15 times 10 to the minus 3, N is 720 divided by 60 here, since revs per minute. And Z is 750 and C is 2 wave 1. So that a very simple calculation comes out to be 270 volts. All right. Any question on that?
No, sir, clear.
All right, good. Another one, and this one is from the Hughes. It says a 4-pole armature has 624 lock connected conductors and is driven at 1200 RPM. Yeah, useful flux per pole required to generate an EMF of 250 volts. No, we should calculate that. Calculate the useful flux per pole required to generate an EMF of 250 volts. So again, pulling out the data, there's a 4-pole, so P is equal to 4. The number of conductors, Z is equal to 624. The generated EMF is 250. The speed at which the machine is driven is 1200 RPM. All right, so again, substituting. So E is equal to 2P phi capital N over 60 times Z over C. And we substitute the data to make phi the subject of the formula. Substitute the data, and phi works out to be 20 milliwebers. All right, so fairly straightforward calculations here. But of course, we're just warming up, right? All right. I think I put another one here. All right, so this one now is asking you to calculate the EMF when the machine is wave wound or when it is lap wound. All right, so just showing you the range at which they can ask these questions. So they can ask you for different things, right? But all of them utilizing the this induced EMF equation. All right, so again, you pull out your data. Z is equal to 1000, number of conductors. P is equal to 4, capital P. Wave one, when it is wave one, C will be equal to 2. So 2P phi NZ over C, 60C. And substituting the data, E is equal to 400 volts. When it is lap wound in E is equal to 2P phi N over 60 times Z over C. And C now would be equal to the number of poles before. So it is, when it is lap wound, the voltage induced in the conductors would be 200, right? So generally, wave wound machines are used for higher voltage application, low current application. And lap wound are used for a lower voltage, high current. Because you have more parallel parts in the lap wound, so you can carry higher current and split them up in each parallel part. So general application. All right, and I think this may be the final question in this unit for class. Next time I will make sure that you actually have something to work out. But you will have some to do for practice later on for homework. All right, so another one, a DC generator running at 25 revs per second. So now we're using the speed in terms of revs per second, generates an EMF of 150 volt. And we should determine the percentage increase in the flux per pole required to generate 180 volts at 20 revs per second. So basically what has happened, we're increasing the speed at which the generator is running. No, not increasing, but decreasing. So it was running at 25 revs, and we have reduced the speed to 20 revs, and we want to see how the flux, how the flux will change as a result of the changes in the speed and in the generated voltage. All right, so if we call the 150 volts E1, so this is where it was first, so E1 will be 150 volts, E2 would be 180, N1 would be the 25 revs per second, and N2 would be the 20 revs per second. So again, we'll write this relationship E1 over E2 will be equal to K phi 1 N1 over K phi 2 N2, and the K's, which you are seeing right here, are cancelled. So phi 2, making phi 2 the subject of the formula because we want to see how the flux has changed, what is the new flux, and how much it has changed. So phi 2 would now be equal to E2 times phi 1 N1 divided by E1 N2. All right, so this will be 1, E2 is 180, 180 times the phi 1 times the 25, N1, 25. And E1 was 150 and N2 is 20. So phi 2 is now equal to 1.5 times phi 1, which means now that the flux has increased by 50%, 0.5 per unit. So it has changed from phi to 1.5 phi. So it has increased by 0.5 per unit, or a 50% increase. So a 50% increase in the flux has caused an increase in the induced EMF. But it's not that alone. The speed has reduced also. So by the combination of both of them has resulted in an increase in UCM. All right. I have listed some questions here. This is not the end of Unit 5. It's the end of Part 1, though. All right. End of Part 1 in Unit 5. There are some questions here that I've listed here that I would want you to practice to get a better feel of utilizing this equation. All right, so this is where Part 1 ends. What I will do is probably take a 5-minute break and then we come back for Part 2. All right, so take a 5-minute break, drink some water, and we start back at 6:20. Starting Part 2. Basically, what I want to do is to see if we can finish, ensure that we finish by next week. So, Mr. Atkinson, we may be able to have another test the following week. Not next week, but the other week.
Okay.
All right. All right, so take a water break and come back.
Mr. Daly.
Yes, Miss Montague.
Sir, have you marked this one as yet?
In the process. Yeah, so some persons have gotten back some feedback. Yeah, I'm still in the process.
Okay, sir.
Trust me, I will. I'm trying my best.
Sir, no pressure.
Oh, thank you, thank you very much. Yeah, I am trying to swim upstream in heavy currents. Okay, are we back?
Yes, sir.
Okay, good. All right, so let's get into part 2. And part 2 again will have more details, but we're gonna look more at generators this time. The DC generators in particular. Different types of connections, shunt, series, compound, and we'll do some calculations on efficiency. Okay, so let's get into it. All right, so the diagram is showing you how the windings are brought out of the machine. So the field windings are F, a positive one, and F1, for the negative connection. And the armature conductor is connected via the brushes, via the commutator and via the brushes to terminals A and A1. All right, now how these are actually connected together will determine the type of machine that we have. All right. At the same time, you should remember that the same machine can be operated either as a motor or as a generator. All right, so the different methods of connecting the field winding and the armature windings are separately excited, or well, our term is separately excited or self-excited. No, a separately excited machine has its own a different source of supply to feed the field winding, while so one source of supply would be feeding the field windings, while another source would be connected to the armature. While in the self-excited machine, the same source of supply would be connected to both the field and the shunt, field and the armature winding, right? So the self-excited machine can be, again, arranged in these forms. What is called a shunt wound, the series wound, and the compound wound machine. All right, and I'll quickly show you circuit diagrams now. So the circuit diagram of a separately excited DC generator is shown here. So a different source of supply would be, so these are not connected together now. The armature is not connected here. So an external source of supply is here. And they'll have an induced EMF being developed across the field, across here, across the armature conductor. And you will have that induced EMF now available to supply a load. Right? So this would be what the separately excited machine, because the field and the armature conductors are not connected together directly here. All right, they're only connected by the flux here. Flux produced by the field winding would be cutting across the armature here. And remember, in a generator, the armature now would be rotating inside that field to, rotated inside the field to create that induced EMF. All right. The direction of the current in the armature winding here will tell you whether or not the machine is a generator or a motor. So the current is actually going out, so the generator delivers current to a load. So the current will be flowing out. So the load will be connected across here. So the current will be flowing out into the load. All right. Oh, there's a note here that although this oval thing here is representing the armature, and this would be basically the armature, and this would be the brushes resting on the commutator. The resistance of the armature winding is shown separate for clarity. So it is just drawn separately. So although it is, it is part of this, it is shown separately for clarity. So that is the usual way of representing the machines, whether self or separately excited, in terms of segregating the resistance, the armature winding resistance from the rest of the armature. All right, so when a load is connected across the terminal, a current IA will flow into the load, and the terminal voltage would be equal to this generated EMF, right, minus the voltage drop across the armature. So right here we have the plus polarity, here negative polarity, but because the current is flowing in this direction, down here will be a plus polarity and a minus polarity here. So that is why it is E minus IARA. All right, so bear that in mind. So I could write now an equation for the induced EMF or the generated EMF. It would be equal to the terminal voltage plus the voltage drop across the armature winding. All right, so that is saying it. But remember now that E is also equal to K phi N. So this E here is also equal to K phi N. So more interesting relationships can come up as a result of that. Ooh, right away into a problem, an example. All right, so so it's basically more of the same, separate, but I wanted to show you an example with a separately excited generator, because after this now we're going into self-excited machines, right? So a separately excited generator develops a no load EMF of 180 volts at an armature speed of 15 revs per second and a flux per pole of 0.2 Webers. So calculate the generated EMF when the speed increases to 20 revs per second and the flux per pole remains unchanged. So the speed R and B when the speed remains at 15 revs per second and the pole flux decreases to 0.125. And then when you have a change in speed and a change in flux for part C. All right, so let's get into it quickly. So E1 at no load is 180 volts, and N1 at no load is 15 revs per second, and the flux is 0.2. And we should find E2 when the speed has gone to 20 revs per second, but the flux has remained unchanged. So since the flux is unchanged, phi 2 would be equal to phi 1. All right, so therefore, these two relationships can be divided. E1, or we could write it as E2 divided by E1 since we want E2, so it's probably easier to have E2 in the numerator here. So E2 would be equal to E1 after you do this mathematics. So E2 over E1 is equal to K phi 2 N2 divided by K phi 1 N1. Works out to be phi 1, since phi 2 is equal to phi 1, I write back phi 1 here. So phi 1 N2 over phi 1 N1. And the phi's again would cancel, just like how the K's cancel here. So I'm left with E2 over E1 is equal to N2 over N1 for this situation. So E2 then would be equal to E1 times N2 over N1. And E1 was 120. So 120 times 20, N2 is 20, and divided by 15. So the voltage has gone up to 240 volts by increasing the speed. The induced EMF has gone up to 240 volts. All right, what happens when the speed remains constant, but the flux has decreased? So N2 will be equal to N1, and that's equal to 15 revs per second. But phi 2 has gone down to 0.125. So again, just manipulating these equations, we end up with phi 2 times N1 over phi 1 times N1. And since N2 is equal to N1, we write N1 here in terms of N for replacing N2. So N1s would cancel. So I'm left with E2 over E1 equal to phi 2 over phi 1. And then maths tell me that the induced EMF has reduced because the flux has reduced. All right. And then quickly, let's look at part C. N1 is 15, phi 1 is 0.2, N2 is 25, phi 2 is 0.18. And substituting E2 equal to E1 phi 2 N2 over phi 1 N1. And the voltage has gone to 270 volts. So increasing the speed and decreasing the flux from the original value. Both of them now has caused an even greater increase in the induced EMF. All right. So these are things that will actually, I would have actually done in the lab too, you know. And I will post the video recording of that lab soon. All right, so self-excited machines now. DC shunt wound generator. The field windings and the armature windings are connected in parallel, shunt, parallel, series. Armature and field windings are connected in series, and then compound. We have various combinations of shunt and series for the compound. All right, so this diagram is showing a shunt generator, and we can tell because we can see the direction of the current going to the terminal. Right? So current is heading out, so we know it's a generator. So the induced EMF would be the source of the voltage, and it is driving that current through the armature current. It also drives a current through the field winding, IF, and it drives a current to the load. All right, so the field winding has a resistance, RF, and the current through the field winding is IF. And as you know before, the armature winding resistance is RA, and the current through it is IA. So the load current is I. All right, now E, from what we had done before, E would be equal to, so these are in parallel now. So I could, since E is the source, E would be equal to this voltage, the terminal voltage, plus the voltage drop. So, right, the terminal voltage plus the voltage drop would give me the E. But saying it better now, E is equal to the terminal voltage drop, the terminal voltage plus the voltage drop across the armature. So if I want to find out what that terminal voltage is, and remember the terminal voltage is what will be connected across the load somewhere out here. V would be equal to E minus IARA, which is what we had found before. And V is also across this parallel branch here. V is also equal to IFRF. And from before, we know that E is equal to K phi N. So basically, just looking at the equations for this circuit, IA would be equal to IF plus I. So I can write a value for I2. I would be equal to IA minus IF. All right, so let us know the machine have particular characteristics or graphs that basically represents them. So the shunt generator at no load, the current is 0, right? At no load, I would be equal to 0. And so we're looking at the no load characteristics. E is equal to K phi N. And flux is produced by the field current. So we're going to be plotting the generated EMF versus the field current. So IF is proportional to the flux, since IF is what produces the flux. And remember, E is equal to K phi N. Now, since it's a generator, N is constant because it's going to be maintained constant by that mechanical prime mover. So therefore, since we have a couple constants, so E is proportional to IF. E is proportional to phi, and phi is proportional to IF. So E is proportional to IF. So I can write, and since N is a constant, it will be included in this constant here. So E is equal to K, call it K1 times IF. All right. So K1 is a constant since N is a constant. So the no load characteristics of the machine is like this. So as we increase IF, the induced EMF is increasing, right? As you increase IF, induced EMF is increasing until it reaches a point where the armature material becomes saturated. So an increase in IF, further increases in IF will only result in minimal increase in the induced EMF, right? So this is where now the armature core is saturating. All right, so for a particular point, IF was proportional, directly proportional to the, or say it the other way, the generated EMF was directly proportional to the field current. But above a certain value of the field current, saturation exists, and then that linear relationship no longer exists. All right. So generally, you would want to operate your machine in the linear portion, so you can actually predict operations. Now, when you load the machine, we're going to plot now terminal voltage versus load current. So the load current is I. So as the load increases, I, as you can see here, as load current I increases, I is also increasing, right? So I guess you could also say that I is a function of the load current. All right. So as the load current I increases, IA also increases. But as you can see here now from this equation, as IA increases, this value here is increasing also, and hence the overall, you have an overall reduction in the terminal voltage as I increases. So that is what is shown here. Right? Now this decrease in terminal voltage is usually about 10% from no load to full load. All right. You can read through these, but the major point is that when you look at this equation, as you increase the load, you also increase the armature current for the generator. And then as you increase in the armature current, you're increasing the voltage drop across the armature conductors, and hence you're reducing the terminal voltage. All right. Now a series generator has the series the field winding and the armature winding connected in series, as shown here. All right. They draw it like this. I mean, it's not necessary to draw it like this. We have this kind of U-shaped thing here. But what they have done basically is to show you that the field winding close to the armature is producing a flux. So the flux is what is going to be causing when the armature conductor is turning, you have an induced EMF across here. But as I say, it's not necessarily to draw it like that. Some people do, some books do, does it like that, and it actually show you the flux flowing across. Series generators are rarely used, but it's used in DC voltage transmission. At no load, I is equal to 0. So no current basically will be flowing in here. And you know, the equation again for the generated EMF is equal to V plus I into RA plus RF. So the terminal voltage V will be equal to E minus IARA. So at no load, V would be equal to E, and E is again equal to K phi N. Right, so at no load, IA equal IF equal I equal 0. Same current flowing through both windings, right? All right, now, so there is an induced EMF at no load, right? And we can see that there is actually a terminal voltage at no load because E is equal to V plus IARA. So even when I is equal to 0, V terminal voltage is going to be equal to the induced EMF. And this induced EMF is due to the residual flux in the field poles. So some residual flux are in the field poles, and as the armature is turning within the field, you have an induced EMF, right? A small voltage. So even at no load, you have a small terminal voltage. across the terminals of the generator, series generator. And as we load the machine now, same current flowing through the armature and the field, and the induced EMF did we point out. So since these are in series, so that's why you have RF plus RA, they're in series, right? So that way the total resistance of the armature and field winding. All right. So again, V is equal to E minus IARA. Now again, I is proportional to the flux, the current flowing through the field winding, and E is proportional to I. Now RA and RF are small for the series machine. So as we increase I, as we increase I, flux is increasing, so E is increasing here. But at the same time, as I's increase, you have an increased voltage drop across here. But this, as we say here now, these are very small, so the voltage drop is relatively small. So we basically have, as I is increasing, E is also increasing. And so we have this linear action until when you reach saturation. All right, so again, that is the load characteristic. So that is the kind of graph you expect when the machine is, the series generator is on load. And then this is the compound where you can have this both a series winding in series with the armature, and then you have the field winding here. So this is one type of shunt. This is called a long shunt. And this is another shunt where the series winding now is moved from this position to here. And the field winding is directly across the armature. So this will be the short shunt. All right. I think I might have an example for a compound machine. Right, yeah, compound generator. All right, so another work example for you. So a short shunt generator, compound generator, supplies 80 amps at 200 volts. So it supply a load with 80 amps at 200 volts. If the field resistance RF is equal to 40 ohm and the series resistance is 0.02 ohm, let's say it was a short shunt, so we know that this would be more closer to the armature. So this is here. And the armature resistance is 0.04, determine the EMF generated. All right, so we can write a series of equations for this machine. The first one is equal to V1, voltage across here, plus IARA. And IA, according to Kirchhoff law, would be equal to IF plus I. And this IF is also equal to this voltage across this branch here divided by RF. So, and then I can write an equation for V1 also. V1 would be equal to this voltage drop plus the voltage at the terminal here. So V1 is equal to this voltage drop plus this voltage across the terminal here. So V1 is equal to V plus I RSE. So V1, we know V here is 200, I is 80, and RSE is 0.02. So V1 then is 201.6 volts. Now from this, we can work out what IF is equal to. IF is V1 over RF. So V1 is 201.6 divided by 40. So IF is equal to 5.04 amps. All right, so we can work out what I is equal to. I will be equal to I plus IF, and IF was 5.04. I is 80, so IA now is 85.04. And we're supposed to be determining the generated EMF, so that would be V1 plus the voltage drop across the armature, V1 plus IARA, and that's 201 plus this 85.04 times 0.04. So the generated EMF is 205 volts. All right, so this one now a little bit more involved, but if you work step by step, you will come back to the solution. All right, a little bit on compound generators. They combine the best features of shunt and series generators, are used in arc welding, in lighting sets, in marine equipment. Right. So this is something that you can read up on. Look at the characteristics. You will see them both in the bird and in the hues. The characteristics for the different forms of the compound generator. All right, I had some applications here for DC generators. They can provide power supply to DC motors, welding machine. We're using automotive industry for battery charging, but basically that has been replaced by alternators. Right? Was used for street lighting. This is a Ward Leonard system. We have a motor and a generator. You can read up on that. Good to know. All right, so let me get into the efficiency of the DC machine, particularly the generator. Right? Now, in general, efficiency is P out over P in.
Sir,
Yes.
so I think we could have pick up right here so next week, sir, because right now we're in a lock off, you know, sir.
Just hold it, open it for a little while. Just a one little while. We only have about 2. We will go back over some of this when we do the generator. The motor. But it's not a lot. At least we want to get the concept. At least I wanted to get the concept. So maybe we can stop here after this page. But in general, efficiency is P out over P in. And P in can be written as P out plus P losses, as we did last week. But the losses in the DC machine are copper loss, core loss, and then there's something called the friction and windage loss. Some textbooks call it the rotational loss. And then you have losses at where the brushes make contact with the commutator. So the losses are described here. So in deference to Mr. Adams, I guess we can stop here. But you can continue reading when your brain unfreeze.
Yes, sir, definitely.
Because
Sir, I would just like to state that I appreciate the fact you understand that our brains froze.
I understand that too. My brain froze from earlier today. So it's working through ice right now. All right, but yeah, we will just remind me where we left off then, because I might forget completely with my frozen brain.
Sir,
All right, sir.
I think the correct term is saturated. We're saturated, sir.
It's an appropriate term, right? A point of diminishing returns. We can actually
Yeah.
show the graph, you know. So the load has increased, but brain not absorbing anything.
Heard that. Yeah, prime example.
All right, so yeah, I will make a note of where we stop, but I know Miss Montague will remind me.
All right,
Sir,
sir.
how you sure that me even know where you stop, sir?
Well, that would be a disaster then.
Madam
All right.
Secretary, come on, Madam Secretary.
All right. Well, the only thing we have to do is go back and listen to the look at the video if we can remember. All right. Yes. So we will call it a day here. Next week we probably need an hour. So it shouldn't be too much. Maybe what I'll do is probably add some questions for you to maybe work out something in class instead of me working out all of the problems. And that will help to unfreeze the brains too. All right, so I will see you next week. I will post the recordings and the video for the DC shunt motor, so you can maybe better appreciate armature and field windings and commutator and all of those things. All right.
All right, sir.
Yes, sir.
Yes, sir.
All right. Take care, everybody.
Yeah, man.
Sir.
Sabusu.
Yeah. Send your email and sir.
I responded to the one I saw today. So I don't know if you want me to make an announcement. No.
No man, sir. That's fine.
You sure? All right. Yes. You can check my email that I responded to earlier. All right. All the best to you and to everybody.
Okay, sir. Thank you.
Okay.